Recording is happening, so you better watch what you're speaking. And let's move to the back, the big camera, famous camera. Ooh, so exciting time. Okay, I'll HD looks very weird, but I'm trying to ignore it. Hopefully nothing bad will happen. For the next exam quiz, I'm not going to do that. Quiz is just a quiz. So quiz is going to be at the end of the class. For the exam, I might maintain the time to be fixed. Like if it is an hour-long exam, it's going to be an hour-long exam, but I might open it up for a longer time, not for like for 3 days or the whole weekend, but I might open it up a little bit longer because it's an open book exam. And I always write a fresh exam. Sounds like one of the Thai restaurants. The guy used to always say that we cook everything from fresh. So when I write an exam, I write an exam from fresh. Yeah. So
can we have the exams be able to go back to our old questions or no?
there was a comment, one of you guys, I don't remember who it was from which class, and she really made a good case that it's easier for me to attempt the easy questions first and then attempt the tough questions, and that's the way I have done it. And I'll be very honest with you, and I'll make a confession that I locked the questions and I made them like one attempt answer just to prevent funny business from happening. But I think I'm going to open it up. I'm going
Just
to
because like when there's a time limit, it's easier to like go through them fast, and then if you have extra time, be able to go back and do like the harder problems. That's just how people test usually. So
yeah,
like,
that's how people test usually, and that's how I test usually. I mean, I will be probably upset if I did that. So yeah, see, conversation can convince a person that I should change. Yeah, we will do that. Anything else? Okay, let's go to the board. Sounds like a great journey. Okay, I'm going to go a little fast, so get used to it. I'm keeping the window open because the sky is blue, and I just want to watch it. By the time we go home, it's pretty dark, so I'm just enjoying looking at the sky. If it is glaring, if it is causing too much glare on this side, let me know. I'll pull the blind down.
It's blurry right now.
Is it blurry?
Yes, sure.
Okay. It's probably blurry. Hold on. I think there is probably a different problem.
The camera.
It's clear, but is the glare causing trouble? Let me write something. Then, if it is a problem, just tell me. I will close the blind. I'm just trying to enjoy the sky that's not brown. I'm not being racist here, okay? I'm very inclusive of all the colors. Back in India, we used to enjoy the colors during dawn and dusk because the air is dirty. It's really funny. And when I came here into US, I'm like, why is the sky so bland in the morning and in the afternoon? I wrote to my brother and I said, and he basically called me an idiot. He said, hey, dumb than something else. And he said, don't you understand that the air is much cleaner, and that's why we don't have all the refractions and we don't see the colors during sunset and sunrise. That's why it's more bland. So I'm like, that's interesting. So I can probably breathe better. Okay, no more chit chat. That's it. We're done. Chem 8, Tuesday, Thursday, fall 20. Not that it's going to change if I don't write this down. And today is 9/24/2020. Okay. I'm going to deliberately write something up here. If it is causing problem, let me know right now. Hydrogen.
Is
it out of focus? I think it's out of focus. That's this camera is driving me crazy. Okay. It is. I think the glare is a problem. Okay, bye sky. All right, that's hydrogen. Okay, and hydrogen is written this way. and carbon is, I'm just going to write 2s, okay? Forget about the core shell at this point. 2s, 2, and 2px. I wish I had a few more fingers. 2py, and 2pz is empty. Oh, sorry. Okay, so this is how I'm deliberately not writing the 1s. So don't get confused, okay? Because it's a core shell, we don't care. Now we know that that's not good enough. This is ground state. This is ground state. And this is not good enough for it to be able to make the bonds, because we know that if this is right, then it's leading to a scenario like this. And let me just color code it. And scenario like this. So therefore, this scenario, this electronic configuration would lead to this Lewis dot structure, and this Lewis dot structure would lead to a molecule that would look like this, CH2. Okay, and we know that's not the case. We know that that's not the right molecule. The right formula of the molecule is, okay, so we kind of work backward. This is kind of like, you don't want to call it cheating, but because we're kind of working backwards. So something happens to the carbon in CH4. What happens? Well, it converts, it jumps. One of these electrons jumps here, and the carbon goes to what is called the excited state. We have already talked about it. So the carbon is in the excited state. Okay, and that carbon looks like this. 2s is still 1 electron. 2p is 1 electron, 2px. 2py has 1 electron. Board is still focused? Yeah, okay. It looks like it. You have to slap it like twice or thrice before it really behaves. 2pz has 1 electron. So this scenario, this is the excited state. So, and it looks pretty good. 4 unpaired electrons at level 2, right? They're all level 2. 2, 2, 2, 2. So they're all in the second floor. Okay, all these 4 people are in the second floor, each in each room. So now there are 4 people, 4 electrons, unpaired electrons. So the Lewis dot representation would look like this. 1 here, 1 here, 1 here, and 1 here. Okay, and this would lead to the formation of CH4 by providing 1 unpaired electron to 4 hydrogens. How would this molecule look like? This molecule would look like this. Wrong location. I need to move it a little bit more to the left side. Okay. This guy, this bond would be a short bond because s orbital is smaller. I'm going to redraw it somewhere here, okay? This is going to be a short bond. This is going to be a longer bond. This is going to be a longer bond. This is also going to be a long bond, okay? And then, you know what? I need to change the color of the hydrogen here. Let's put this color so that we can kind of fit it here. There is going to be a hydrogen, there is going to be a hydrogen, there is going to be a hydrogen, and there is going to be a hydrogen. So supposedly, this or these all these orbitals are, these electrons are coming from this electron, this electron, this electron, and this electron. Okay, all these 4 electrons, they're coming from 1s orbital, another 1s, another 1s, and another 1s. This guy is coming from, this is a 2s orbital, that electron. Okay, this electron is coming from a 2p x orbital, this guy. Okay, this guy. This electron is coming from, is provided from 2p y orbital, and this electron is provided by an electron sitting in the 2p z orbital. Okay, so expected shape should be 3 long bonds and a short bond. Then it turns out that's not the case. It turns out that all 4 CH bonds are identical. So now what I'm going to do is I'm going to draw the real carbon hydrogen bonds are same length. Okay. This is reality. This is 1s, this is 1s, this is an electron from 1s, this is an electron from 1s. And we really do not know at this point what's going on here. Okay, they're supposed to be 3 long and 1 short, but they're all equal. This is experimentally found. Experimentally. Okay, and so time to scratch our heads and look at the sky and think, like when we went to Heidelberg in 2015 for a conference, first time in Europe, though, just a beautiful town. Didn't feel like coming back to Fresno. I'm just being honest. It's just a beautiful town. There's a river, there's a cliff, there is a mountain, there is a fort, like, I don't know, very old, the very famous university. People are pretty nice, lots of good food. You can walk around the whole town. There was a place called Philosopher's Point or something up on the hills where people, like famous philosophers, would just sit there. They probably didn't have to worry about making money, teaching or working and earning money to bring food. They probably had enough support. They would just hang out there and think about stuff. So this is one of those moments, like scratching head and losing hair. So what can happen? So the bottom line is these electrons, whatever these electrons are not different kinds of electrons. This is the bottom line. In CH4 or in a molecule, carbon has 4 electrons that have identical properties. Okay, that's the bottom line. Like, you better fit your theory to the problem. This is the result. You fit your model, you fit your theory to the model. That's what science does, right? You see something and then you try to figure out like what could be going on, right? So the bottom line is all these 4 electrons are identical. Their length, shape, everything is identical. So this is not right. So what we say, I mean, it's actually a very simple solution. We say that, well, if that's the case, then carbon, when it's making bonds with somebody else, the electrons are kind of getting mixed up. Like 1 part, what did I say? Beef and 3 parts of bean. and the mom is putting them together in a casserole with some sauteed onions, making me hungry right now. I just had some cereal. We decided to switch breakfast and lunch for some experimental and convenience related driving forces. So the mom put them together and made four bowls of chili, right? So it's just that simple. 1 part S, 3 parts P. They go in a blender. You run it for like 2 minutes, and whatever comes out of it looks pretty disgusting, right? But then it tastes pretty good. So you divide it into 4 identical parts, and you get 4 sp3 orbitals, hybrid orbitals. So here, this is where hybridization happens. Hybridization happens. What is hybridization? When you hear the complex word hybridization, it's like a hybrid car, an ICE engine, internal combustion engine, gasoline engine, mated with an electric engine and an electric motor and an electric battery, right? That's how it functions. Right now, I'm trying to fix an old hybrid car by regenerating the battery. It's a 2000 Honda Insight with a stick shift. That was the first hybrid car ever launched in this country. I love that car because it's a manual transmission. So I'm just trying to fix the battery. So the battery provides enough electrons to the motor. The electric motor and the gasoline motor make it a hybrid car. So hybridization means basically mixing gasoline engine and mixed with an electric engine. So hybridization, think mixing. It's just that. So what are we mixing? 1 part S and 3 parts P, and the hybridized carbon has now 4 electrons in 4 hybridized orbitals. Each orbital is called sp3 orbital. Okay? And they look and behave exactly the same. Their length, their shape, their orientation, they are very similar to each other, okay? Because they're the same level, that means they have the same energy, right? So when this guy bonds with 4 hydrogens, all the 4 CH bonds are identical. And the reason it's called sp3 is because we could have called it s1p3, but we don't say it. Just drop one thing less so that we don't have to deal with it, right? Chemists, we are all trying to use abbreviations and symbols and stick diagrams. We will learn when we learn alkanes and alkenes and alkynes, like how you not write carbon, how you not write hydrogen, but we get the point across that, oh, we are talking about C2H6 or CH3, CH2, CH3. We just don't write everything down. We have developed some kind of a secret, like some kind of code, okay? 4 sp3 orbitals because 1s went with 3p. So 1s, 1p, second p, fourth p. So if you put 4 orbitals before hybridization, at the end of the hybridization, you get out the same number of hybridized orbitals, okay? If 4 go into the blender, you get 4 hybridized orbitals. If you put 3 of them together, you get 3 orbitals. We'll talk about that in the double bond stitch scenarios. For single bond, triple bond scenarios, you just mix 2 orbitals. So far, so good? Take a quick look. Maybe we'll take like a 10-second break.
Professor?
Yeah.
Would it be okay if you repeated what you said right now, but if you add 4 into the
Yes.
What did you mean?
So when hybridization is happening, you're mixing a bunch of orbitals together, right? So you're mixing, in this case, we are mixing 1 s-type orbital and 3 p-type orbitals, right? How many orbitals, how many parts of food is going into the blender? 1 part beef and 3 parts bean. How many parts of components is that? 1, 2, 3, 4. 4 parts, right? So after you mix 1 part beef and 3 parts bean, you end up making how many bowls of chili? 4. So because you used 4 parts of ingredients, 3 parts of chili, 3 bowls of chili, and 1 bowl of beef. So you end up making 4 bowls of chili. I don't know what I said. 1 part beef and 3 parts of bean, you end up making 4 parts of chili, right? So 1 part S and 3 parts P, they mix together to produce 4 hybridized orbitals, and they're called sp3. This 3 means 3p orbitals. Nothing means 1s orbital. That's, imagine that there is a 1. So far, so good. Any other questions? Did I answer your question correctly?
Yes, thank you.
So there's 3 P's because it's an excited, or isn't there usually 2 P's for carbon?
Usually there are 2 electrons in the 2p state, but after it went to the excited state so that it can unhinge one of the tangled tentacles, right? Imagine carbon looking like this. That means 2 of its tentacles are tangled and 2 of its tentacles are free to pick up a couple of crabs. And carbon wants to pick up 4 crabs. We should probably drop my metaphors. Probably confuses you guys. So if this is a crab and this is an octopus, in this case, the carbon has 2 of its tentacles kind of like tied together. So you're supposed to untangle it. When you untangle it, you are freeing up this paired tentacle and dumping it in the pz orbital. So now you have 3 electrons in the 3p shells, not shell, orbitals, 3p orbitals. So you are providing for hybridization, what are our ingredients? 1 orbital, 1 electron in s orbital, 2s orbital, 1 electron in pz, 2pz, 1 electron in 2py, and 1 electron in 2px. So 3 electrons in 3 p orbitals and 1 electron in 1 s orbital. So how many electrons are going into the blender for hybridization? 4. 1, 2, 3, 4. 4 electrons. So if 4 electrons are going in 4 orbitals, different kinds of orbitals, 2 kinds of orbitals, small and dumbbell shaped. So when you're producing the product, you're producing the same number of products, 4 hybrid orbitals. And they're called sp3 because it's 1s and 3p. So I'll just write this down. So this means 1 s orbital and 3 p orbitals. That's what it means. So that 1 is not written and that 3 is represented here. I'm glad that you're asking. For some reason, as I said, hybridization is not something that goes very well. It doesn't sit well with you guys for whatever unknown reason that I cannot explain. Okay. So now at this point, now this carbon, I'm just going to erase it because I need that space. It's not going to be a big deal. So now the carbon is ready to make 4 bonds with 4 hydrogens and make 4 identical bonds because they got mixed up and the resulting electrons around carbon are identical. They're looking identical. So how would the molecule look like? CH4. After this guy, this hybridized sp3 hybridized carbon forms bonds with 4 hydrogens, right? 4 hydrogens come, 1s, another hydrogen comes with electron here, 1s, another hydrogen comes with another electron, 1s, and the fourth hydrogen comes with its fourth electron as 1s, okay? Now, what we are writing here is the molecule. This is the CH4 molecule. Let me just clean it up a little bit because it's not looking so good. CH4 will look like sp3. This is an sp3 orbital, sp3 orbital, sp3 orbital, and sp3 orbital. Okay, this is an sp3 hybridized electron, sp3 hybridized electron. So each electron has the property of 25% s and 75% p. Okay, this is a hybrid orbital because it has the property of little bit of this and 3 times p orbital. Okay, so it's a hybrid orbital. So in CH4, the hydrogens are in. Now this is CH4, not just the carbon. So hydrogens are now in, and they're paired up. This might confuse you. Just give me some time. So this is sp3 of carbon and 1s of hydrogen. sp3 of carbon and 1s of hydrogen. sp3 of carbon and 1s of hydrogen, right? So this whole thing is a CH bond. So this is a CH bond. 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 And this is a CH bond. So now this is a covalent bond. This is a covalent bond right down there. So this is a covalent bond. This is a covalent bond. And this is a covalent bond. So each pair of electrons, you might be wondering, like, carbon only has 4 electrons in the second shell. Why do we have 8 electrons? Well, this thing represents that, and that, right? Each paired electron is representing a CH bond in methane, in CH4. That's one of them is this bond, second one is that bond, third one is this bond, and the fourth one is that bond. I'm going to take a pause for maybe for a minute and let you guys kind of swallow it. Not swallow it, just digest it. What's a better word? Something like that. I'm going to just also draw the hybrid orbitals, the different angles. So X, just for a reminder, Y axis, where is my Z? Right there. And the Z axis. And the X orbital, the 2p orbital is here in the middle. That's 2p. Not 2p, 2s. Misspeaking too much. That's an s orbital. I misspoke again. That's a 2px orbital. What am I talking about? I think I need to retire and be a shepherd for local goat growers. You'll see me up on the mountains. This is 2py, and this is 2pz. Okay, this is how the 3 orbitals look like. One s, one px, one py, and one pz. When they mix together, you can clearly see that the s orbital is small. Therefore, it's supposed to be making a small bond, and the p orbitals are longer. They're supposed to be making a longer bond. but we already discussed it. That's not how it is. In the real life scenario, methane has been found to have 4 identical bonds. Okay, 4 identical bonds. In order to explain that problem, that why does it have 4 identical bonds, that's the theory that chemists could come up with. Chemists said, well, there must be some mixing going on here because all the 4 electrons are identical. It's actually a very simple theory if you think about it. Like, it's really like a foolish theory. Like, oh, because it has the properties of both, they're probably getting mixed up somehow. So they're getting mixed up, and they're producing 4 identical hybrid orbitals, sp3 hybrid orbitals, and now 4 hydrogens come and make 4 bonds with 4 hybrid orbitals of oxygen, carbon, and then they're producing 4 identical CH bonds. I'll try to keep my mouth shut. You can feel free to ask questions if you want. Go through it sequentially. Carbon is born this way, gets excited, because if it doesn't get excited, we cannot explain why this happens, not that happens, that doesn't happen, right? Remember, one of the fundamental requirements that you need to understand is that 1 chemical bond, 2 electrons. So in order for you to make 4 chemical bonds, you cannot use this pair. So I'm going to just write it down here, just for the sake of it. This pair, not useful to make bond. The unpaired electrons, this is good. This is useful. This is useful. This is of no use. It's already paired. In order for you to make a bond between me and somebody else, I need to provide 1 electron. That person has to provide 1 electron. Now we have a shared covalent bond. If I have 2 electrons right here, if I have 2 electrons, these 2 electrons, the lone pair, I cannot make a bond with somebody else's 1 electron. Okay, so that's what carbon is doing. It's going from the ground state to the excited state by unpairing, untangling, like disconnecting the two electrons from each other. They were paired like this, up and down, and now it's going up and going into an excited state. Carbon would like to be this way because this is how it's born, less energy. But in order for it to make bonds, it has to sacrifice. It has to go up to a higher energy level. That's the excited state. Okay, 1, 1, 1, and 1. 4 electrons, but then 1 is tiny and the 3 are different. So then hybridization happens. So far, so good. No question is a bad question. All right. If there is no question, what time are we at? 1:26. This is good. Okay, as long as I can complete the hybridization, this is good. Okay. So now, I don't want you to see what I'm doing right now. Okay. Let's say I'm going to just draw the molecule in 1 color. Okay. If each carbon-hydrogen bond can be represented as a little plastic stick, right? Another stick, another stick. I'm not that flexible. Another stick, okay? If these are the 4 sticks, okay? How do you think their shape is? Are they flat? Are they like this, hanging together like a little, they're all parallel, very close to each other? Or they're forming like a tripod? Okay, not tripod, quadrupod. Is it like this? Or is it like a tripod? like a camera's tripod with a little thing where you can put the camera, or there three of them are like this, and then one is like this. What do you think the shape is? I just want you to think about it and not make any, not take an initiative to give me an answer. Just think about it. Then after like half a minute, I'm going to give you one more piece of information. So we're trying to figure out what the shape of this molecule should be. If you already know the shape because you have read it up or you have learned it in the past in general chemistry, try to control your urge to speak. Just lay low right now. Lay under the radar. Okay. Realize that when we have these CH bonds together, right? When we have the CH bonds, this is all, there's a lot of electron cloud here, right? One electron from carbon, one electron from hydrogen, two electrons, and two electrons. Lot of electrons. Okay. What have you learned in physics? Even if you haven't taken any physics, a positive charge and a negative charge. What do? Do they attract each other or do they repel each other? Opposite charges, do they attract or do they repel? Speak up. Don't give me a thumbs up or something. What do opposite charges do?
Attract.
They attract, right? So electron, they're everywhere electrons, right? So when you have two electrons in this bond, two electrons in this bond, two electrons in this bond, and two electrons in this bond, right? There are a whole bunch of electrons. What do you think will be the mutual feeling of each bond to the other with respect to the other? Are they going to be attracting each other or are they going to be repelling each other? Is this going to be a great scenario or they're going to try to stay away from each other as much as possible? Are they going to repel or are they going to attract? Bunch of electrons in 4 bonds. What do you guys think will happen? I'm definitely going to drop one pretty soon. You guys can almost see all of them. 4 CH bonds, are they going to repel each other or are they going to attract each other? If they're going to attracting each other, you know what's going to happen. The molecule will fold into like a parallel 4 pipes in a row and CH, 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 CH. Is that going to be how it's going to look like? Are all the electrons going to be like one on top of each other, like a litter of puppies?
No.
No, they're going to repel.
Yeah.
Okay. If they're going to repel each other, now I'll allow the person who has read the book. If they're going to repel each other, and if they're all connected to the central point, do you know what the shape is when they're farthest away from each other? What is that shape called? It's a T word. I guarantee that more than one person in this class knows that word. What's the word for the shape? When 4 bonds are attached to the central focal point or fulcrum, and they're repelling. So this is actually a great experiment if you have the toys at home. If you have 4 bar magnets, actually, I don't have it. If you have 4 bar magnets, not super powerful, like weak bar magnets, if you could tie the north poles or the south poles together in some kind of a little, I don't know, some kind of a device, okay, if you could put them together, not like fix them with super glue, but in a flexible way, the 4 north-south bar magnets will adopt this shape, which has a specific name. What is it called? It's a T word. Who knows?
Tetrahedral.
Tetrahedral. Tetrahedral is done by this. Now I can bring out my secret other piece. This is the tetrahedral carbon. And when I attach the sticks, it's going to be easier for you to see it. And I'll give you like a really decent perception of tetrahedral, what tetrahedral, nobody did that to me when I was at the receiving end in India as an undergraduate organic student. I wish somebody had told me that, then it would really stick to my brain. So I'm going to give you a perception of what tetrahedron looks like. This is a tetrahedron, okay? Before I talk about the shape and how to draw a methane, this is a two-dimensional representation. This is a two-dimensional representation, okay? 2D. How does it look in 3D? That, before I talk about that, how to draw a methane molecule in that way, I'll give you a perception of what is a tetrahedron, okay? You kind of know what is a tetrahedron. Yeah, so 4 bar magnets stuck together at the same pole in the center, that the shape that they're going to adopt is a tetrahedron. There's an easier way to imagine this. How would you do that? Well, imagine a cube, an Amazon box. Usually they're not cubical. Imagine a cube. I learned it in India, actually. So I'm really thankful. Whichever book, I don't remember which book it was, or was it like an instructor who talked about it, or my brother who talked about it. He was basically trying to rescue. FYI, I screwed up my undergraduate, whether you believe it or not. Most of my students will not believe. Like, oh, you're a professor. I'm like, yeah, I mean, I came a very long way. I had a 2-year of dark phase where I thought my life was pretty much done. But I kept at it, and with some help, I was able to get out of that hole. So I have screwed up before. This is a box, cubical box, and you place the carbon in the middle. Carbon is in the middle, okay? When you put the carbon in the middle, I'm trying to keep the same colors. You put the 2 hydrogens, 2 of the 4 hydrogens at the 2 corners, the diagonal corner. So I put 1 hydrogen here. I put another hydrogen here. And the 2 other hydrogens, if I'm in the middle of the box, and if this is how the box is, this line is parallel to you guys, to the board. This is vertical, and that's parallel. You put 2 hydrogens. You put 2 hydrogens here and here at the 2 corners, there and here. And the 2 other hydrogens, you put them kind of crisscrossed with those 2 hydrogens. You put the other 2 hydrogens, I don't know if you can see it, down there and here on the opposite ends. So they're crisscrossed, okay? The hydrogen-hydrogen bond on the top and the hydrogen-hydrogen bond at the bottom, they're at 90 degrees. So these 2 hydrogens you put here and here. Then you connect the dots, okay? So this bond, if you think about it very carefully, I'm going to erase these dotted lines. If you think about this bond, it's kind of in the, if this is the box, I don't really have a box here. I don't have a box. I wish I had a box. So if this is the box, okay, if this is about this deep, the carbon is in the middle, okay? And this hydrogen is here. This hydrogen is here. So the bond from the carbon to this hydrogen, let's number them. Let's call them 1, 2, 3, and 4. It'll be easier for us to see. So the central carbon to this hydrogen, that bond is kind of sticking out toward you. When a bond is sticking out from the center, it's moving toward you, we use a wedge. That means that bond is sticking out. So this is something that we usually teach in chapter 5 in stereochemistry, but I'm talking about it right now, 1:37. We still have like 8 minutes. So we are talking about something, and you will find that although it might sound like we're going at a snail pace, but you are learning things all over the board. So when we are in stereochemistry, when we are learning stuff from that chapter, you will find that a lot of things will appear much, much easier because you've already been exposed to it. So I'm kind of justifying my speed right now. That's all it is. And this hydrogen, this corner of the box is way further down. This corner is behind the whiteboard, okay? Because if you think about it this way, if this hydrogen is, if this guy is right here, and this guy is right here, and the carbon is here, so this bond is coming toward you, and the hydrogen number 2 is down here, that bond is going behind the whiteboard. The carbon is already behind the whiteboard and it's going even further behind. So that bond, the bond that's going behind, going backwards, that's usually drawn with a dashed line. Okay? These two bonds are pretty much on the plane. So I'm just going to draw a straight line here and a straight line here. Okay? So if you now compare the molecule, okay, I know that this is purple and this is not purple. I don't really have 4 purple bonds. I only have 2 purple bonds. Yeah, it's useless. So if this is the carbon, okay, if this is the carbon, these are the hydrogens. That's hydrogen number 1, hydrogen number 2, hydrogen number 3, and hydrogen number 4. So you just learned a convention. When the bonds are on the whiteboard or on your screen or on the whiteboard or on the screen or piece of paper where you're writing, you draw them with solid lines. Okay, solid lines. When the bond is sticking out from the paper, okay, if this is the sheet, if that's the screen, your computer screen or your tablet screen or the piece of paper you're writing it, if this bond is sticking out toward you, you write that with a wedge, as if it's kind of coming toward you, like getting bigger, right? Objects that are nearer to you, they're bigger. Objects that are farther away in the mirror, they're smaller, right? So this part of the bond looks big and fat, and this part of the bond looks tiny and small. Same deal here. When the bond is going backwards, you kind of draw it with dashed lines, like as if it's fading out in the distance, right? It's like you can well, it's not exactly true because we should have maintained the size like big to small, but that makes it kind of weird just from our perception. So we usually write the small dot dashed line and it gets bigger and bigger, bigger and bigger. It's not entirely correct, right? If we can argue about that, but let's not argue. Let's keep going. Okay. So this is how you draw a molecule in 3 dimension. And this shape is called tetrahedron. Tetrahedron is the noun, and tetrahedral is the adjective. We say it's a tetrahedral carbon. Tetrahedral is the adjective. Okay, we say tetrahedral carbon. And the way we write it, this is 2D, the way we write it is the following. 2 bonds, solid, means that means it's on the same plane. 1 bond out and 1 bond in. This is out, this is in or behind, and these 2 are on surface. Not my computer surface, but the surface, okay? So solid lines on the surface, wedge coming toward you, kind of like pointing out at you, and dashed line means behind you, okay? This is how it got way too unclean. I'm just going to draw it again, okay? This is methane in 3D. This is how you do it. All this knowledge was probably not supposed to be taught in this chapter, but then you will understand that it's going to be helpful. Okay. So where are we right now? 43. I think I'm going to take a picture and I'm going to call it a day. I don't think I have much more stuff to talk about today. I wish I had covered a little bit more, but that's fine. I think the discussion that we had at the beginning was much more healthy than talking about chemistry and trying to, like shove more material. I'm really happy that we had that discussion at the beginning. So I'm going to upload the video. I'm going to upload the picture. I already started making keys of the quiz and the exam. I'm kind of late on the quiz, so my bad, forgive me. And see you guys on Tuesday. Have a good weekend. Enjoy and maintain your sanity. Take care of your children, parents, yourself. You need some time out. Maybe you can go for a walk, whatever works for you guys. Pick up a hobby. I mean, some simple hobby, maybe, I don't know. One of my students, I just got a text from her. She's a dental student in Arizona. She's bored, she's lonely. So sometimes she bought some stuff to sew, practice like how to do some fancy sewing. So I have no idea what that means. But she said, I'm learning to do that. She ordered some stuff on Amazon and doing that. You might say that, Dr. Maito, that's a luxury. I don't have the time to do that. I understand. Just stay afloat, eat healthy, and have some fun. Maybe you should bother somebody else in the family for your own entertainment. I do that all the time. So how much I bother a person, that tells me how much I like that person. If I don't care, then I normally will be like, I'll never bother anyone. So, all right, have a good weekend, guys. Good chatting with you. And if you want to have a meeting tomorrow, more than welcome to do that. I'm going to just switch to the front camera for some time. Anybody else? Anything else? Anyone is having a great lunch today? Don't make me feel bad. Questions? I know somebody wants to ask a question. Angelus?
I was just gonna say that I think my lunch is gonna be cereal.
Cereal is good. Maybe it'll help. Maybe I'll finally lose 15 pounds. I just started eating cereal. All right. Bye, Carlos. Bye, Ivan, Angelus. Take care. Have a good weekend. Anybody has any other questions? I'm not trying to shoo you off. No?
No, I was just gonna say have a good weekend too. Thank you.
Bye. Take care. Good seeing you.